Question 7, evaluate the limit as n goes to infinity of n divided by n plus 1 to the n. Let's call this L. So now we can say we're looking for L. So the first thing we're going to do is pull back this theorem from section 10.1. If the limit as x goes to infinity of f of x exists, then the limit as n goes to infinity of a sub n is equal to the limit as x goes to infinity of f of x if a sub n is equal to f of n. So this basically says I can replace the n's with x's here. So really what I'm going to look for is this is the limit as x goes to infinity of x over x plus 1 to the x. So if this limit exists, and we'll show that it does, these two will be the same limits. Okay, so this is still going to equal L here. This is basically, at this point, a Calculus 1 problem, but it's a very common Calculus 1 problem, so I'm going to crunch through it. So the thing to realize is that if we let x go to infinity, x divided by x plus 1, that's getting close to 1. But the exponent we're raising it to is going to infinity. So right here, we have what we would say is a 1 to the infinity indeterminate form. Okay, so how do we handle indeterminate forms? Well, in general, we want to use the L'Hopital's rule, but right now we're not in a 0 over 0 or infinity over infinity indeterminate form right now. So it's going to be a little bit of work that we have to do before we can get to a point in which we can use the L'Hopital's rule. Okay, so how do we manipulate it into a form that in which we can use L'Hopital's rule? The trick is we're going to take natural log of both sides here. So we're going to say natural log of L is equal to, now we can do the following tricks here. We can move the natural log inside the limit, and then the whole reason that we can that we want to take natural logs here and move it inside the limit is to allow this exponent here, this x, we be able to bring down that exponent. So after making all of these changes, so limit as x goes to infinity of natural log, we move the natural log inside the limit. We're allowed to do this because natural log is a continuous function. We're basically using the function limit version of this in a couple different ways in this problem. So natural log of x divided by x plus 1. So bring down the factor of x. So it was up here, and that comes down here. Okay, so what's going on in this limit? Well, as x goes to infinity, this x is going to infinity, and x divided by x plus 1, well, that's still getting close and close to 1, and natural log of 1 is 0. So we've gone from a 1 to the infinity indeterminate form to now we have an infinity times 0, a 0 times infinity indeterminate form. So we've managed to manipulate one indeterminate form into a different indeterminate form, but we're still not at a point in which we can do L'Hopital's rule yet, because we're not in a 0 over 0 or infinity indeterminate form. So we have to do one final manipulation before we're allowed to do L'Hopital's rule, and that is, instead of multiplying by x, we're going to move it to the denominator. So dividing by 1 over x is the same thing as multiplying by x. This looks nastier, but now we are in a position to say, hey, as x goes to infinity, x over x plus 1 goes to 1. Natural log of 1 is 0. And as x goes to infinity, 1 over x, that goes to 0. Now we are in a place in which we can use L'Hopital's rule. So use L'Hopital's rule, and that will do the trick for us. So let me go to a new slide here. So once again, we have natural log of L is equal to the limit as x goes to infinity of, going to make one other cosmetic change that will just make the calculation a smidge easier. Natural log of a quotient here, natural log of a divided by b. This is natural log of the numerator minus natural log of the denominator. It'll just make my life a little bit easier when I go to take the derivative of it. This will be a little bit easier to take the derivative of. Okay, so here's L'Hopital's rule. Okay, derivative of the numerator, 1 over x. The derivative of natural log x is 1 over x. Derivative of natural log of x plus 1 is 1 over x plus 1. And the derivative of 1 over x in the denominator is minus 1 over x squared. Okay, so let's put all of this together. How can we simplify this? Let's put this over a common denominator. So we would get cross multiplying gives us x plus 1 minus x. Cancel, 1 over x times x plus 1. Going from 1 over x times x plus 1 to 1 over x minus 1 over x plus 1, that's something we do a lot with partial fractions, especially in the telescoping series case. Here we're doing that in reverse. And dividing by minus 1 over x squared is the same thing as multiplying by x squared. So we end up with minus x squared times 1 divided by x plus x times x plus 1. Those x's cancel. The limit as x goes to infinity of minus x divided by x plus 1. It's pretty easy to see that that's minus 1. Use L'Hopital's rule again or something like that. And so what's our conclusion here? Is this our final answer? Okay, leading question, the answer is going to be no here, because natural log of L is equal to minus 1. So that tells us that L is equal to e to the minus 1, which we can rewrite as 1 over e. So our final answer here is going to be 1 over e. To quickly summarize, what's the big things of this problem? Number one, knowing to take natural log here. Well, I guess number one is rewriting everything in terms of x and realizing this is just basically a Calc 1 problem. Number two, realizing that we have a 1 to infinity indeterminate form, take natural logs, and moving that natural log inside because it's continuous, bringing down the x, knowing it's infinity times 0 indeterminate form, knowing you have to still do a bit more manipulation, and then I suppose rewriting the natural log of x divided by x plus 1 in this form makes your life a little bit easier. And then, oh yeah, don't forget to go back to your final answer isn't minus 1, it's e to the minus 1.